All right, a couple of announcements before we get started today. Of course, you know that Friday I will not be on campus at all. Normally I have office hours 7:45 to 11:45. This Friday, not. I'm supposed to be at the clinic by 6:30 for labs and start treatment at 7:30, and they say it's going to go probably 7 hours. So, yeah, it's going to.
My grandmother's going to be up there at 8:30.
On what?
On Friday.
On Friday? Oh, okay.
But I don't know if it'll be the same area.
Yeah.
It's the
Second floor?
I can't remember.
Right.
It's an IV.
Yeah, infusion.
It was infusion therapy or something.
Yeah, exactly. That's the same place.
Well, you might see.
Okay. If I'm not already asleep by then.
Well, I told her, if you see a tall, goofy man.
What's that? Oh, I see. Thank you very much. Okay, very much. Okay.
Worst things to call you.
You probably have. Okay.
No.
All right. So I won't be here Friday. Now, here's the other bugaboo. Next Tuesday, I have an appointment with my hematologist. He's the one who only sees patients on Tuesday mornings. So therefore, it's almost definitely going to kill this course, and probably linear algebra too. And the odds are it's going to wipe out, my 112 also. So I've got 3 classes to make up. And I talked with and now the thing is, I don't know exactly what time. I'm thinking the appointment is either 8 or 8:40. If it is, then I might be back for linear algebra. I just don't know. Okay. I kind of doubt it, but I might be. Okay. So I talked with my first class, and I'm going to let them know on Thursday, if we make up the class, they wanted to do it Thursday afternoon at 12:30. So that will be one long 4 back-to-back classes. Okay.
So you have 112, then DPQ, then linear algebra, then 112 again.
Yes, exactly. Okay, that'll be.
I said let's just skip the makeup and keep going.
Well, I hate to cheat you out of your tuition dollars, but if we can make it up, we can. We will. Like we did last time, have one double one day and one double the next or something. But we'll do that. But they've already claimed dibs on that. I kind of like the idea of 1 o'clock better because it gives time for lunch, like you say, and still has time. So we'll see what we can do. But several of them did have 12:30 open, so I said, let's go for 12:30 then. And there won't be many here, so we'll just record. Okay, that done. And of course, that messes up office hours for pretty much this week and next week, and maybe even to the following, but whatever. And I guess you do know it's sort of a good news, bad news situation. The bad news is the following Friday is Veterans Day. So the college campus is closed in. But the good news is we won't mess with this class any. Okay. So we won't lose any.
It's okay.
Yeah.
That's perfectly fine.
Okay.
I'm happy with that.
All right. All right. Where we were is in 4.2, reduction of order. Okay.
Yeah, you're right at the beginning.
What's that?
I said, yeah, right at the beginning.
Yeah. Suppose that Y1, let me get the slideshow set up from the current slide.
Yeah, I wouldn't ask me about what to redo classes today. I'm just too apathetic.
What, long night or something?
Something like that.
Yeah, okay. All right. Suppose that Y1 denotes a non-trivial solution of this equation. A2 of x, y double prime, plus A1 of x, y prime, plus A0 of x, y is equal to 0. Okay, now, just as a quick review, that's a linear second order homogeneous differential equation, right? Because it's equal to 0 on the right. Okay, so we're saying that y1 is a non-trivial solution for that.
So basically, not everything equals 0.
Right. Okay. Because obviously that in the homogeneous case, y equals 0 is a solution. Because then y equals 0, y prime could be equal to 0, y double prime is equal to 0, the sum of those will equal to 0. That will be a solution, and it's one of the solutions. But this y1 is not that solution. There could be up to 2 other solutions, remember, because it's a second order. No, up to 1 other solution. So it's the non-trivial. Okay. This is the one that's not the trivial case. Okay. N is defined on some interval I. Okay? We seek a second solution, y2, okay? So that the set consisting of y1 and y2 is linearly independent on that same interval, okay? So I was right before. There are at least 2 more solutions. y1 is 1. We're looking for the second one. Recall sorry, section 4.1, that if y1 and y2 are linearly independent, then their quotient, okay, if they are linearly independent, okay, then that means their quotient, and which one they put on top, y2 over y1, okay, is a non-constant. Okay? In other words, if they were dependent, one's a multiple of the other. Okay? So if they're independent, they're not going to be, the ratio can't be a constant. It's got to have some x dependence or y dependence or some dependence. It just can't be a constant. Okay?
But if they were dependent, it would just be a number.
Yeah, that ratio would be a number. Exactly. Okay. So if it's non-constant, let's call that u of x. Okay? Where there is x dependence. Or another way to write that is y2 is equal to u of x times y1. Right? And y1 is a function of x, and y2, by the way, is a function of x as well. Okay? Now, the function u can be found by substituting in here, okay, into the given differential equation up here, okay? If we figure out what y2 is, we know it's got to be that. It can't be a constant. U can't be a constant. So we can go through and do all the things and find out what it is. That method is called reduction in order because you must solve a linear first order equation in order to find u. Okay? That's what you would do. You do y2, y2 prime, and y2 double prime, plug back into that and set it equal to 0. That's the procedure. Let's do one. All right. All right. I think I'll clean the screen. Okay. And let's do, given that, and this, again, irritates me. Why don't they show you how you get these rather than just say, given that y1 is equal to e to the x, okay, that is a solution of this differential equation. Y double prime minus y equals 0. You need to verify that? We can do it fairly quickly.
No, e to the x minus e to the x is 0.
Yeah, exactly, because the first derivative is e to the x, second derivative is e to the x, e to the x minus e to the x is 0. Yes, that's verified. We know that is. Okay, we also know there has got to be some other solution. And that, by the way, that's good on the interval negative infinity to infinity. That's good everywhere. Okay. Now it says use reduction in order to find a second solution, y2. So the y2, a function of x, is going to be some u of x times y1, which is e to the x. Okay? Right.
And then we're going to take the derivative of that.
That's exactly what you do. y2 prime of x is going to be what?
Would it be u prime?
U prime of x
U prime of x?
times e to the x plus product rule. U of x e to the x. Okay?
We took the derivative of e that
Huh?
time. We took the derivative of e to the x that
Yeah, it's that time, yeah. In case you were blinked your eye or something. Okay. So let's do y2 double prime of x.
u, another double, it's like a double product.
Okay?
So
Okay.
u double prime of x
U double prime of x
e to the x
e to the x. You didn't take the derivative that time. Okay?
plus
Plus
u
prime of x
times e to the x.
e to the x. You did take it that time.
And then plus
Plus,
the same thing over. No, it would be the last thing, right?
say that again.
What we had for the first derivative. Just
Yeah.
copy it over.
Okay, and that would be u prime of x e to the x plus u of x e to the x.
Sorry, I'm lazy.
Right? Which is u double prime x e to the x plus 2 u prime x e to the x plus u to the x of x e to the x. Now, I'm really wanting to pull out those e to the x's, and we will in just a second.
Now we got to plug it back into that formula.
Okay. Yeah, plug this into our formula up there. So that would be y2 double prime, which is this, u double prime of x. I'm just going to pull out the e to the x. I'm tired of writing it, okay? Okay, e to the x times u double prime of x plus 2u prime of x plus u of x. Okay, that's the double prime part. Minus the y, this is your y2 up there, which is u of x e to the x. Okay, which, and this has to equal 0 for that to be a solution. Well, notice this one and that one wipe out. So that both times e to the x. You had u to the x for the first one and a minus u to the x for the second one. Okay? Right. Okay? So, yeah, just the first part. E to the x times u double prime of x plus 2u prime of x has to be equal to 0. Okay, I know. I couldn't tell because the pen was so far behind, I couldn't tell if I'd written it or not. Okay, now, that gives us, okay, time out. E to the x can never be 0, right? E to the x is never 0.
This is going to be kind of silly.
What's that?
I said, I think this might be a silly question, but what equation do we plug back into again?
Okay, when we did,
After we got the second derivative.
right, we plugged into the differential equation. Y double prime minus y equals 0.
Okay, and we took y2 double prime.
Yeah, y2 double prime and y2.
Y2
Yeah.
equals 0. Okay. You don't mix the y1s and y2s in that.
Right. Yeah, we already knew y1 was 1.
Right.
So now this. Well, e to the x
You can divide it out.
cannot be 0. So that means this thing has to be 0. Okay? U double prime x plus 2u prime x is equal to 0. Okay? Got to be. No question about it. Okay? So I'll write it down. They did too. U double prime of X plus 2U prime of X has to be equal to 0 for that to work. Okay. Now, this seems bizarre, but it's fine. Yeah. Let's let W equal U prime. Okay? Okay? This is to reduce your power, reduce your order. Reduce your order. Okay? I mean, we just made up U anyway, so let's make up a W, okay? It's going to be U prime. So this is one of the tricks, yeah. Then W prime is equal to U double prime, right? Okay? So our new equation is W prime of X plus 2. All right, here's Victor. All right. We're on page 130, in section 4.2, and what the title of this section is reduction of order. Okay? We had order in here. You came in and you reduced the order. No, I'm just kidding. That's not what happened. Okay. We didn't have any order. No. Okay.
You know what's funny though?
What?
We're halfway through the section now.
Yeah, I know. I know. This is a very short section. I like it. Okay. And we're on example 1 on page 130, in the top half of the page still. And we've got W prime of X plus 2W of X is equal to 0.
Wow, that pen is lagging behind.
What's that?
The pen is lagging.
Yeah, it really is. Pretty slow. All right. Now, it's a linear first order equation in W, obviously. Okay. Now, since it is a linear first order equation in 0, okay, if you go back to chapter 2, yes, remember, 2.3, I believe it is, linear equations, and remember that's when we did the integrating factor. Okay? Remember
Yeah, you gotta find
yes,
the
exactly.
raise
Okay.
it, the integral of that to E, and then you find
Right. All right. So what we do here, I don't have much room left, so what I'm going to do is do a bunch of erasing.
you probably erase most of that.
Yeah, that's what I was thinking of doing. I think we're through with the Y2s for now. I hope so anyway. I hope we won't need that again, but if so, we'll go back and retrieve it. It just won't be printed on the page. Okay. Okay. Now I hope I haven't erased anything that we will need. I'll have to go back and reproduce it if we need it. Okay, so there's sort of our new equation. Okay? Now, going back to what we did before, remember we had an integrating factor. Okay? It's going to hold the place, and I didn't wind up holding it. It was 2, 3. Okay. We said integrating factor of mu of x is equal to e to the integral of p of x. Well, our p of x here is simply the number 2. So it's the integral of 2 dx, right? Okay, because your coefficient down here, your p, is the constant function 2. Okay, so this mu of x now, not to be confused with u of x, okay, is the integral of dx is x, so that would be e to the 2x. Okay, that's your mu of x. Okay, now what did we do with that? We multiplied it by our function here, and we had e to the 2x dw dx plus 2 times w of x. Oh, wait. Sorry, I left off my integrating factor. Okay, 2 times 2, e to the 2x times w of x is equal to 0. Okay, that's what we did. We multiplied by that. That was our integrating factor, both sides of the equation. Now this basically sets up a product rule. Okay, and what's the product? This is the derivative with respect to x of w of x e to the 2x. Now, if you don't buy that, just do that derivative and see what you get. That'd be a w prime, which is this, e to the 2x, plus w times 2e to the 2x. Now,
So
this thing,
you didn't really have to rewrite that as dw dx. You could have just left it w prime.
you could have, yeah. But I thought, it depends on what you see and understand best. They use that notation back in 3.2, 2.3. Yeah.
You just changed it. I was making sure there wasn't a reason for it.
Right. So the change of this function with respect to x is 0, which means this thing right here is a constant, right? Okay. So that would mean that if you integrated both sides of that, you get that w of x e to the 2x is equal to some constant. I want to call it C1? Why not? Okay. Now, let's now divide both sides by e to the 2x. Okay. And that gives you your w of x is equal to C1 e to the minus 2x. Okay? So there's your w of x. Okay? Now, and I thought I was going to need this, and we do. Remember, w is u prime. Remember? That's how we got their w. That u prime is equal to C1 e to the minus 2x. Okay? Which is du dx, right? Is equal to C1 e to the minus 2x. All right. And if you were to integrate both sides of that, or in other words, rewrite this in differential form is what I did. Okay, that would be u of x would then be, integral of that would be the C1's on the outside. Yeah, quit doing that. Okay.
You'd have a -2, or wait, no, hold on, I did that backwards. That would be e to the negative x.
No, not quite. That would be, let's do a substitution maybe. Okay, I don't want to use you. Quit. Okay. How about V? No, yeah, we haven't used V yet. Let's let V equal minus 2x. Then dV is equal to minus 2 dx. Okay? So dx is equal to minus dv over 2, or negative 1/2 dv. Okay? Then this integral would be the integral of e to the v, and you'd have a minus c1 over 2 dv, right? Huh? Okay. All right, and that integrates to be e to the v. Okay. So you have u of x is equal to minus 1/2 c1 e to the v, but v is, I know it's here somewhere. There it is, e to the 2 minus 2x. Okay. Plus some other constant, c2. Okay. What's that? Huh?
It makes sense.
Okay. All right. Now the other constant c2. Well, what goes along with that? That could be, remember, at the very beginning. Here was your y1. Now we have the c1 and c2 sort of backwards, but c1 goes with the y2, and c2 can go with the y1, which is now your function y from the beginning, and this is y as a function of x, okay, is equal to negative c1 over 2 e to the minus 2x plus c2 e to the x. Come on. Okay, there we go. And that's your solution to that differential equation. Okay? And you can plug in and go back and see and make sure that verifies that that's good for all x's from negative infinity to positive infinity.
So just a general, what we did, we had what y1 was.
Yeah, they gave us that.
They gave us that.
Yeah.
And then we got y2, and we took a derivative of it, took a second derivative of it, plugged it into the equation, simplified it.
Right.
Once we got that, we found we went back to 2.3, right? And found the substitution, I forget what it's called now. Integrating factor.
Right.
Plugged that in and everything. Simplified that down.
Right.
We substituted for W at some point to get it to where we could do that because we had it in the second order, we needed it in the first
Right.
order.
Exactly.
So we could use that.
Right.
Did that. And then after that it kinda got fuzzy.
Okay. So you came up with a W
Right?
of this using the integrating factor of this. Okay. Then you went back and said that's your first derivative of u,
Right.
which was the ratio of the two.
Went backwards so we could start getting
Exactly.
closer back to what we
Right.
wanted.
And then when we finally got that, we got the u of x, and when we came up with the second constant there, when you had integrated that a second time, that constant goes with the first y. Now that sort of is the smelly part. What gives you the right to do that? They just say thus. Okay. Now,
You just go back and plug in for your
okay.
for when you had y2 plugged into the original equation.
Okay, there is a problem here, though. I'm sorry. I skipped a step. That's why it was smelly. Okay. Let me go back and redo that. Okay. This part was true. Ooh, didn't erase. Okay. Let's go back and redo that. I just plugged it in because I thought that's what they were doing. I said, why can you do that? You can't. Okay. What you're doing here is remember what U is. U is, I wish I had left it now, it's y1 times U is y2, right? Okay.
Well, u of x was in the formula type thing.
Okay. Remember we said, yeah, right up at the beginning, your y2 is equal to u of x, not to be confused with mu of x, times e to the x. Okay? So, this is our u of x. Right. Your y, and remember your, I'm trying to see where we dropped off our y. I guess this could just be your y2. Okay, we can change that to y because that's exactly what we're doing here. That y of x, we were calling y2, now we just go back and call it y, is equal to u to the x times, this is our u to the x times e to the x. So that would be a minus 1/2 c1, okay, e to the minus 2x times e to the x, right? Because you're multiplying it by e to the x. That would be e to the minus x. Quit. Okay. Plus c2 okay, e to the x. All right, there we have it. That now is our thing. The multiplying by our e to the x, which they gave us to begin with, that gives a general solution here.
All right, so yeah, so the u of x we found to be negative 1/2 c1 times e to the negative 2x plus c2. We
Right.
went through and multiplied that through by that
By the e to the x from here,
so
right?
this is
Yeah.
y2.
And this will be not just y2, it's y in general. Your y of x is going to be that u times e to the x. That's what gives it to us. Okay. There's your general solution. Okay. Two constants because we had a second order linear differential equation. So we need to have the two constants. Okay. Now, then, if that wasn't enough, they say by picking out C2 is equal to 0, why would you do that? You have Y2 is equal to, yeah, and then they also choose C1 to be a negative 2. They just pick what suits them, okay? or e to the minus x. You had the -2, negative bound. C1 is -2, and it's a minus in front of it. So yeah, that makes it positive. Okay. Now, remember our good old Wronskian? If you don't, that's just a few sections back, page 122. The Wronskian is you put the functions and first and second derivatives, or as many as it takes, and do the determinant of that. Okay? So, and it sort of drives me nuts. They chose W, but now they're capping a capital W is a Wronskian. So the Wronskian of these two functions, I think they put e to the, no, they put e to the x first. It doesn't matter which one, but I'm going to try to do it the same way they do. E to the minus x. Okay. That would be, okay. Your, on page 122, you see if you have two functions, you need it to be a square matrix, basically, right? And you put F1, F2. We've only got two, so we only do e to the x, e to the minus x, e to the x. This is first derivatives on the second row, minus e to the minus x. You do that derivative, that determinant, and that would be a -1 when you multiply these two together, minus another -1, that's -2. So your Wronskian here is -2. Okay? It doesn't matter what it is, it's just not equal to 0. Okay? So that does show these two are linearly independent. We didn't need to do that. You can look at them and tell they're not linearly independent. They're not dependent.
So they came out and picked the C2 and C1. I think I see how or why they did that. They just took the they took the y of x and set it equal to the original.
Right. Well, basically, what the reason for doing that is to set up your y1 and y2 to be the simplest forms you can. E to the minus x and e to the x. Okay. You can have any other linear combination of them, but what they're wanting to show is those two functions are linearly independent of each other. And so just pick the simplest combination that gives you that, and then you could do the Wronskian with what you had before, but it's just a lot messier. So use the C1 and C2 to get it in the simplest form you can. If they're linearly independent there, they're linearly independent anywhere. Okay. So now we've shown that y1 is equal to e to the x and y2 equal to e to the minus x are linearly independent solutions of a linear second order differential equation that we had. And it's actually the general solution if you put in your C1s and C2s, whatever they need to be. And here's the key. Okay? You see this coefficient here? It doesn't have to be a -1/2 C1. Just make that C3. It's just a constant. Okay? So now you have linear independence. Well, I'm sorry, I did the wrong one. It's this one down here. And this one's already just a constant. So rename them or whatever. Those are your independent functions.
Basically, picking anything to make it a non-trivial solution, but as simple as possible.
Right, exactly.
So you could have, I guess you could have gone C1 is 0 and then C2 is 1.
C1, 0. It's C2 with 1. That would give you your e to the x. And
trying to make sure that there aren't some certain rules. If I did something different, it'd be breaking things.
Right. All you're looking for is the functions that work. And I mean, as soon as you got this, you didn't have to go through and set them. You could just say, rename this to be some other constant, C3, because negative 1/2 of a constant is still a constant. So it doesn't have to be that. So basically, you got a constant times this plus a constant times that. That's your general solution. Okay. They had to choose a weird way to do it, but it still works. So here's the general case. Okay. Okay. Let's go back to our original equation that we had at the very beginning. A2 of x, y double prime, and that's a function of x2, plus a1 of x, y prime, plus a0 of x, y is equal to 0. The second order linear differential equation, homogeneous equation. Okay, so that's what we're starting with. That's the general case. Now, suppose you divide everything by the A2. Okay, and let's do that. A2 of x, A2 of x, A2 of x, and we divide 0 by A2 of x, still 0. Okay, so this gives you y double prime, because that goes to 1, plus, okay, now, this is still some function of x, okay? It may not be a polynomial function, probably isn't. It's a rational function, but it doesn't even have to be that. It could be any kind of function, but it's a function of x. We're going to call that p of x, y prime, plus, and then this is some other function of x, and they call that q of x times y is equal to 0. Okay? What's that? It does? Okay. Okay.
It's just the variables that makes me think.
Yeah. I think polynomials when I see it, and that's why I said it's not a polynomial, because usually capital P of x means polynomial. It's not. Don't even imagine it is. Okay. But all you've done there is gotten your linear coefficient function out of the picture. I mean, the second derivative coefficient function out of the picture, divide them so you have other functions of x over there. This is now that standard form we used in section 2.3. Okay? And that's why they did the p of x, because then, okay, this is called the standard form. This was what we were using. We convert it to this, and we call this our standard form. Here are some of the criteria that have to be met by that. The p of x and q of x must be continuous on some interval I. Okay. Now, especially since you divide it by a2 of x, that makes you think there could be some vertical asymptotes or something in there. Well, you have to just pick your intervals so they don't exist, because vertical asymptote would indicate non-continuity. So you just have to have that. But guess what? If that was 0, this would be a second order differential equation anyway. So I think you're fairly safe in doing that. Okay? And then 2, you're divided by this, and the odds are you're not divided by 0 anywhere from here either. So yeah, it's probably pretty good to say P and Q are continuous on some interval I. If you have to pick the interval, pick it, Say it can't be negative infinity to infinity. It may be from 1 to 7, or something like that, some interval where you don't have any vertical asymptotes or discontinuities or anything. Okay, so that's the first thing. P and Q must be continuous on some interval I. Let us suppose further that y1 of x is a known solution of that equation. This irritates me. They ought to be showing you how you get that, but they're going to do that later, but we'll live with this now. Okay, so that we know that y1 is a known solution, and that y1 is not equal to 0 for every x on that interval. Okay, then define y. So we're calling y2. Okay, second thing, y1 of x known from somewhere out of the blue. Then your y of x, they were calling y2, now they're just calling y, is equal to some u of x times this y1 of x. Okay? That's going to be your general solution. Okay? Then it follows from, yeah, we've already done all that stuff. My head is just all clogged up. We really do, I guess, need to do all the steps here. Then let's do y prime is equal to u prime of x, y1 of x, plus u of x, y prime, y1 prime of x. Okay, that's your product rule. Okay, and then your y double prime, very similar to what we did before. Exactly what we did before, exactly. Except remember before, it was a of x's now, and they're not quite the same, but you know, this is just sort of a review of that. y1 of x plus, let's go on and make this 2 u prime of x, y1 prime of x, okay, because that incorporates the first one before, plus u of x, y1 double prime, no, yeah, double prime of x. I was skipping steps. I hope I haven't done anything stupid here. Okay, this is this one times that, and then you have u prime, y prime, one of them, and then you have another u prime, y prime from here, and then you have a u times y double prime. So that gave you exactly what we had before, I think. Yeah, okay. Now, when you put that in the original formula here, then this will be a u double prime y1 plus 2u prime y1 prime plus u y1 double prime. That's your y double prime here. That's that one. Okay. Plus your p of x, whatever that turned out being, remember it's this thing up here, whatever that was, y prime, and your y prime is u prime y1 plus u y1 prime. Okay? Plus q of x times y, which is u y1. Okay? And this has to be equal to 0. Just plug those things in there. Now, okay. Now, right. Now the next step that we do here, okay, after we've done that, is separate the u's, the u double primes, and the u single primes. Group the terms together. So I'm going to start with the u double prime. That's only multiplied by y1. Nowhere else have you got it. Okay? Plus 2u, let's see. I'm going to change this ever so slightly. I hope it's ever so slightly. U prime times 2y1 prime from here plus p of x y1 from there. And those are the only two there, right? That's your u prime terms. Okay? Plus your u terms, and your u terms are y1 double prime plus p of x times y1 prime, right? Okay. What I'm doing, okay, this line, I hope you agree, is true. I mean,
Yeah.
okay, you got it?
Yeah.
Okay. Now I'm pulling out all my u double primes.
Right.
That's the only one. That's it.
Second one, you pull out the.
Then pull out the u prime, which will be a 2y1 prime plus a p of x y1, and that's it for that. Now pull out the u, and that will be this one. That's a y1 double prime plus a p y1 prime.
I just didn't have my parentheses in there, and I was looking at mine trying to find where you were getting
Okay.
it.
And then you have a q of x plus a q of x y1. That's equal to 0. Now, remember that y1 was known to be a solution. And if y1 is known to be a solution, then y1 double prime plus p1 y1 prime plus q y1 has to be equal to 0, right? So this one's equal to 0. But that's because that is a solution, that's 0, okay? So basically what that did for you was wipe out that term for you. And now you can go to the w's. Again, it's just what we did before, but now it's doing it in this form. This is now, you can do a reduction, let w be u prime, and you've got the very thing that we have here.
Wait, would the u be left over or no?
Say again?
Would the u be left over from that equaling 0?
No, because this thing's always 0 because of this. Okay, so that's always 0.
So 0
So
times that,
you've lost that. So now you've just got this as your differential equation, and u double prime and u prime with no u in it. So make this w and make this w prime, and that's exactly what we did before. Okay. But now it's in this form rather than the other form that we had. This is a general case. The previous one was one particular case. This is the general case. Now, I need to erase a bunch. Okay. No. Why will my eraser not come up? There we go. It came up that time. All right. I hope I don't need this anymore. Okay. And I just sort of want to hang on to this next one. And might need that one. But then I don't think I'll need this anymore. We've done it so many times. I don't think we'll need that. I don't think we'll need this anymore. We might, but I hope not. Okay.
As long as you just leave that bottom line, we should be fine.
Yeah, I think that's all we need. Just need not to dip down and erase some of it by mistake. There we go. All right. Now, this implies that we have this left over, y1 u double prime plus 2y1 prime plus py1 times u prime equals 0. That's what we've got at the bottom. Okay? And then if you do, let w equal u prime. Yeah. Then that becomes, okay, then that implies that w prime is equal to u double prime. Okay? And this will then be, I'm going to rearrange and write it the same way they do. y1 w prime, u double prime is w prime, plus 2y1 prime plus p of x y1 times u prime, which is w, is equal to 0. Okay? That gets it into the w. Okay.
And then we can pull out, do the e to the p thing.
What's that again?
We can do, what is it called again?
Oh, yeah, okay, yeah, but let's see. Let's kind of not do that for now and do a slightly different thing. Okay, what we're going to do now is divide both terms by w. Okay? And maybe both terms by y1. Okay? And what you have here is dw over w is equal to minus, if you move that to the other side, 2y1 prime plus p of x y1 over y1. Okay. Now, we can fix that up a little bit better by doing this. Dw over w is equal to minus 2y1, let's call that dy1 over y1 plus, or minus, okay, p of x, that's it. Okay. See what I did there? Yeah, I did a separation of variables. Okay. Noticing that the w prime and w can get together, y1 and y1 primes can get together. But carrying just a little step further, this dw over dw is equal to minus 2y prime over y1 prime over y1. So I wrote that as that. Okay? But then when you do this term, the y1s go out, and that's just minus p of x. So this is a function of w. This is a function of y1 with a constant function. Oh, not constant function. A function only of x there. Okay? Now, and perhaps I went too far on it. What I did, and they've really gotten, I think, a little sloppy here. the dw was dw dx. The w prime, this w prime is dw dx, okay, because x is your independent variable. Now, yeah, what's bizarre here is your y prime is also dy prime dx, but they're ignoring that kinda, okay, and when they did this, they put their dx over here, you know, in the differential form. So to do this, then this would be a dx here and a dx there. And then they integrate this for w, but integrate these, that's a pretty ugly integral, isn't it, with respect to x. So this gives you a log w, okay,
they put it in differential form, but they're still
I know. They skip some really big steps here. Okay. Let's hold off this for a minute because they're skipping a bunch of steps here. Let's do this integral first. Okay. This one. It's a -2, and this is the integral of y1 to the -1 but that's a dy1. See, this is the part that I find they just blow right past this. Okay. Yeah. Okay. Let me go back and see if I can recreate this. I know it's sloppy. Yuck! I hit the eraser and then nothing happens. Okay. Let's go back to that equation up here. Okay. And this is where let me write it the way they did. I was trying to separate the variables, but you still wind up with a px. So let's go back and put them back in, not quite separate. You separate them, but leave them as one equation. Okay, that sounds bizarre, but this is dw over w. Okay. I'm going to go back further. Yuck. Okay. I'm just going to pretend we didn't even do that one. Okay. Because I think we're okay now. All right. Let's take the one that we've got there when we divided, by w's and y1s. Okay. And rewrite this. This w prime over w is dw over w I'm going to take it back one more step, okay, because otherwise it really does look confusing. Okay, let's write this as dw dx, that's what your w prime, times 1 over w. Probably I should write the 1 over w up front. It doesn't matter where you put it. Okay, plus 2 dy1 dx, that's your y prime, I'll put 2 over y1 out front because that's where it wound up to, plus p of x y1 Yeah, let's just then get rid of that. Px plus px is equal to 0. Okay. Now, what they're going to do next is write that in differential form and put the dx out there. So this is a dw over w plus 2 over y1 dy1 plus p of x dx equals 0. Okay? Now, they don't write it that way, and I don't know exactly why. Okay? But what they do is, and it's legal, it just doesn't make a lot of sense to me why they did that. I'm going to change this term to make it match theirs. Okay? Let's go back and call this 2y1 prime over y1 dx. Okay? It's just taking what was there but rewriting that as y prime. They didn't write the w that way. They put that in differential form. Okay. Now here's what they're going to do here. They're only going to integrate this one. Okay. Integrate that with respect to x. Okay. And that integral would be 2 times the integral of y1 to the minus 1. I still want to call that dy1. I think I'm going to do that. It's see, they skip the step in there and they just jump right to the next one. Okay? So I'm going to go back and do, I'm going in circles here because I'm trying to find out the best way to write this. Okay? No, wrong one. Okay. dy1 over y1. Yeah.
See, I was looking at it as a problem.
Yeah. I think this will do it for us. This is log w, right? This is plus 2 log y1, right? If you do that integral or that integral, okay? And then you have plus the integral of p of x dx equals 0. All right. Well, think about what this is saying. This is log w plus log, I can't write, y1 squared plus the integral of p of x dx equals 0. Okay? Well, let's combine those two. And they give you, this gives you w y1 squared because the log of a product is the sum of the logs, right? And that's how they got to that next step, plus the integral p of x dx is equal to 0. That's how they got to that next step.
I'm still hung up on the second integral there.
Okay. This one right here?
Yeah, because I still see that as a quotient rule or a
No,
product.
okay. Forget this one. Go back to all that. Yeah. This is dy dx
Right.
over dy1 dx over y1. But this dx wipes out that, and that just gives you dy1 over y1. Okay. That's what I was trying to do, is they kept throwing it in there. I said, that makes it so confusing. But if you did it like I was going to, in other words, the very beginning there, multiply, write it in differential form. That gives you dw over w plus 2 dy1 over y1 plus p of x dx equals 0. Okay, so that gives you that. Okay, then integrate this with respect to w, that's log of w. Integrate this with respect to y1, that gives you 2.
You can rewrite that as dy1 over y1.
Yes, exactly. Yeah. Oh, yeah. Okay.
That would probably make it.
That, yeah, that's what I wrote here.
Okay. Yeah.
Okay.
That wasn't clear.
There. And that gives you then log of y1 plus 2 log of w plus 2 log of y1 plus that equals 0. Well, rewrite this as log of y1 squared. Rule of logarithm.
I got everything after.
Right. And then you get this. Okay. So let me erase a bunch of stuff, especially the immaterial stuff.
We've gone over.
Right. Like, let's get this one out of there. No, that's the one I wanted to keep. This is the one I wanted to get out of it. Yeah. I don't know. Okay.
We've pretty much run out of time.
Oh, we have.
Yeah, we're like 4 minutes over.
Okay. Well, it's real close here. You have a log here.
Yeah, and then
Let me just sum it up here. We have log of w y1 squared is equal to minus the integral of p of x dx. Okay? Right. And then take the e of both of those, and this would be w y1 squared is equal to e to the minus integral p of x dx. And that looks just like your integrating constant, okay? And then go back and plug in what w is in terms of u and your c's and stuff, and you get the final solution of, let me just write it down. I think we can wipe out this. Your final solution would then be this. Y, which I want to, they say y2. Yeah. There's so many steps they skipped here. 2 is equal to y1 of x. That's the one you knew to begin with, times the integral e to the minus integral p of x dx, okay, and that's divided by y1 squared of x, okay, dx. Now, to me, it's magic how they jump from there to there. If you take it through gradually, yeah, you can come up with that. But what a pain in the neck, okay. Let's do example 2 next time. Start with that next time. We'll be through with this one and look at example 2 next time. We'll be through. I mean, I thought easily we were going to finish this today, but it really turned into a quagmire. Homework exercises, you can do any of the odds 1 through 15. Try 17 or 19. No, let's wait on 17 and 19 until after we do that last example. Okay. Whew, what a pain.
I feel like this should be a 4 credit hour course.
Yeah, it really should. All right, we're going to end this.